So based on the discussion that we have had till now, we are ready to write down the general solution for a n-dimensional system which is undergoing some small oscillations near its equilibrium configuration. Okay, so for a n-dimensional system, so if you take the Lagrangian and from that you write down the equations of motion, this is what you're going to get. So our equation of motion would be Tij, that's your kinetic energy matrix, Qj double dot, of course you have second derivative, and then you have the potential energy term Uij, Qj, and this is equal to 0. Okay, I can write the same equation in matrix form, so the same thing looks like this. Let me write it down on the right hand side. So let me denote by this T the matrix corresponding to these elements Tij, and then we have Q double dot. Q is a column vector plus U, okay, it's a matrix again, and then you have the column vector Q, and this should be 0. Okay, and what we want to do is we want to write down the general solution for Q. Now that's not difficult now because we have already done most of the work. In fact, we have done all the work. All we have to do is just write it down. So what we'll do is we'll recall that our system behaves as if it is a collection of n independent harmonic oscillators. Okay, I'm assuming all the frequencies to be non-zero here. All the oscillators have non-zero frequencies. So the picture is the following. So this system now, if you choose the normal coordinates, then it looks like the following. Maybe I should use some. Why it doesn't work? Yeah, okay. I mean, these pictures they're not necessary, but they do help in remembering certain aspects. So here. Okay. So you have your system appearing as if there are, under the right choice of coordinates, it appears as if you have several harmonic oscillators, one-dimensional harmonic oscillators. Okay, and each of them will have a different frequency, and I am assuming that they are non-zero right now, and this will be the coordinate Q. Okay, remember this is just a cartoon, so Q n, so n oscillators, and these Q's will give you the coordinate which characterizes the displacements. Okay, very nice. So now it's clear what the general solution would be. It would be just a linear sum of all these normal coordinates. Now what do you have at your hand when you disturb the system? So you can think of that you're disturbing your system in such a way that you choose to oscillate the oscillator capital Q1 such that it has a phase phi1 at time t equal to 0 and some amplitude. Okay, so it will have its own amplitude and some phase. This one will have its own amplitude and some phase and so forth. Okay, so those are the things which you control. Okay, they depend on the initial conditions, right? Because given a one-dimensional oscillator, that's what the freedom you have in choosing, which means the following, that the kth normal coordinate I can write as ck e to the I omega k t, and I should take the real part of it. Okay, ck is complex, which encodes the amplitude and the so let's say I write ck, not here. So the phase part of ck combines here and gives you the phase of the oscillator k, and the amplitude here, the radial part gives the amplitude. Okay, so that's what your normal coordinate k is. Okay, and we already have seen that the transition from your q, small q, okay, these coordinates, to the normal coordinates is through a linear transformation. Okay, which means I will write down, let me use q. Okay, I should use black. So my q j, okay, the displacement qj will be the following. It will be a linear sum of all the one-dimensional oscillators, and they will all come with some coefficients. Okay, xi j k. So there is a summation over k implied here. Maybe I can make it explicit. Okay, and these xi's will be determined by us. I mean, we have to calculate. We don't have a control over what xi is. That should be clear. See, what you can control is what is ck. Okay, and ck is two quantities basically. The so if I write ck as some ak e to the I phi k, so you can control what phi k is, what ak is, the amplitude and this. But beyond that, for a one-dimensional oscillator, there is nothing for you to choose. And if you can reduce your system to n oscillators, each of them one-dimensional, you correspondingly choose the phi k and ak for each of them. And beyond that, you have no freedom left to choose anything. Okay, which means that this xi is completely determined by the problem itself. There is nothing for you to choose. Okay, that's the point I wanted to make. I will remove this now. Okay, good. Yeah, so which is basically, I can write this as xi j k times real part of, maybe in the next line, xi j k times real part of ck e to the I omega k t. Note that your xi j k, all these elements are also real. They have to be real because your qj's are real, and this part is real, so this has to be real. Otherwise, your displacements would not be real. Okay, and I have already made the assumption that I'm taking all the omegas to be non-zero. Now I take this qj and substitute in my equation of motion. Okay, so substitute in the equation of motion. And what do I get? I get the following. So you already have a summation over j in this implied here, which I have not made explicit, but now I will. So I had summation over j and then I have a summation over k. Okay, then your Tij here, Tij, then you have your, I have to substitute kj. I take the second derivative, which brings the I omega 2 times, which gives a minus omega k square. So I get xi j k, then your real part of minus omega k square, then you have a ck here, then you have e to the I omega k t, and then you have your potential energy term, which gives you the following: uij, maybe in the, I can write down in the next line, plus uij xi jk, and then real part of ck e to the I omega k t. Okay, that's what you have. We can collect certain terms here and write it in the following fashion. So from here, so now I have summation over k, and I'm going to use matrix notation. So I'm going to write the summation over j using matrix notation. So this Tij is our matrix T, okay, and xi jk, so it's basically xi is getting dotted into the T, that's the product. Let me write down, and then maybe it will be easier to see what I am trying to say here. So minus omega k square T xi of k, I'll tell you what xi of k is in a moment, plus u xi of k, okay, fine, wait, yeah, I should have, it's fine, no problem. E to the, sorry, this is c k e to the I omega k t equal to 0. So let me tell you what xi k is. Your xi k is a column vector. You see, xi k, this xi k does not carry two indices, doesn't carry j k, it's only one, so it's a different quantity. And what I have done is I have defined xi k as a column vector, column, column vector whose jth element. So if you look at this vector and look at its jth element, this is xi j k. Okay, that's the definition of this column vector, xi k. Okay, and if you see this result, this expression, okay, we have a sum over k, and on the right hand side you have 0, and each term corresponding to each k comes with a coefficient ck, which you control, okay, and everything here in this curly brackets is not controlled by you. So if this entire thing has to sum up to 0, it better be that the term in the curly brackets vanish, otherwise it is not possible to make it 0 for whatever ck you choose, because ck's are in your hands, okay. So for that to happen, this quantity in curly brackets should vanish, and let me write it down. So this implies that your minus omega square. I'm just dropping the k for a moment, not for a moment, I'm just dropping it. Okay, so the following should happen. So t xi plus u xi should be equal to 0, okay, because your ck's are arbitrary, determined by the initial conditions. Okay, so that's what the xi should satisfy. As I was saying earlier, here that these are determined by the problem, the xi k's, and that's what you see now, that the xi k's are determined by this equation. Okay, I've just suppressed the index. And you will see immediately why I have done so. Okay, and this equation which you have here, let me write it slightly differently. You can write it as u of xi as omega square t xi. Okay, this is called a generalized eigenvalue problem. Okay, the normal eigenvalue problem would be like u of xi is equal to some constant times xi. It is a normal eigenvalue problem, but this is what is called generalized eigenvalue problem. Instead of having your right hand side being proportional to xi, you have a constant and again a matrix times the xi. Okay, this is called generalized eigenvalue problem. Okay, now you see, if I give you a system and ask what are its characteristic frequencies, what are the frequencies of the normal modes, you do not have to first put the Lagrangian in as a sum of squares, which the way I was telling you earlier. Okay, you can simply do the following. You look at this equation, okay, and from here we can conclude how to find out the eigenfrequencies. And it's simple because these are a set of linear equations. Let me write it down in the following form. I write it as omega square t minus u, okay, xi equal to 0. Okay, these are linear homogeneous equations. Okay, how many of them are there? These are how many equations? Okay, please supply the answer here. Now if this set of equations has to have a non-trivial solution, meaning a non-trivial xi which will make this happen, then it is necessary that we should have determinant of omega square t minus u equal to 0. So if you can solve this equation, which is a polynomial equation of degree what you find here, okay, and then you can solve the polynomial equation and get the characteristic frequencies. Okay, so this will give you okay, it may also happen that some of your omega square turn out to be 0, but that's fine. Okay, now let's say I want to write down the most general solution to our problem where the frequencies are non-zero. Then it would be just this qj's. Okay, so your most general solution is q. Let me write down the solution in the matrix notation. So q is a column vector here. So you had a qj xi k jk. Now this will become column vector xi of j. Okay, and these are anyway here. So your most general solution is the following. And let me make the summation over k explicit. Also, I would request you to check that this problem, okay, if you are looking at this generalized eigenvalue problem, the xi of k in our case is a set of eigenvectors which are orthogonal to each other. Okay, you will be able to do this based on the discussions which we have had in the last couple of hours, or you can also refer to some book like Goldstein. Okay, so yeah, so we have written down the general solution, and we'll continue with more discussion on harmonic oscillations or small oscillations in the next video.